Good afternoon, everyone. Thank you for being here. I'm James Uanhoro, an assistant professor in the Department of Educational Psychology at the University of North Texas. And my specialization is measurement, applied statistics. I mostly work on educational and psychological data. And I know nothing about dementia, cognitive impairments, but I have learned a lot of things in the last day. This breakfast today, I learned so much. So I'm very excited to learn more about the kinds of data you work with and the kinds of problems that you encounter over the course of the next few days. For today, I'm going to talk about bifactor models. And as I understand it, they're relatively common in analysis of some of the data you deal with. So talking about them. And I'll talk about them with, I'll bring in some regression and some Bayesian inference into this talk, try and put all three things together, see how successful that is. Part of the reason for that is my background. So I have a PhD in this field, educational measurements, psychometrics, and all of that. But before that, I had a computing background, and I came into the field. And I heard everybody talk about latent variables, latent variables, latent variables. Everyone talked about them. They couldn't stop talking about them. And the models were always fancy, lots of diagrams. And I'm like, what's this? At some point, I just decided this is all magic, latent variable magic. I had the luck of studying under a professor, Paul DeBook, and he tries to frame latent variables very clearly as regression models. So that really influences my approach to thinking about measurement models. And I'll share some of that today. So they are no longer magic as far as I can tell. I think so. So I'll talk about regression for unidimensional scales, and we'll get to what that means soon. Cover a bit of the challenge of local independence, which then suggests structures like bifactor models as a solution to that. Go over some applications that show some of the application of Bayesian inference to measurement models and close. So that's the layout for today. So the general reason we are talking, the big thing here is dealing with constructs, right? So I think it's relatively easy to say some construct exists. Sometimes there's debate, but usually we can agree that there's something called depression, or there's something called cognitive ability of different kinds. What is hard is actually identifying the construct. So saying depression is A plus B plus C plus D. That's hard. That's a hard problem. And the current standard in the fields I'm used to, education and psychology, is to gather multiple indicators or reflections of the construct into a scale that allegedly measures the construct. So we can't get at the construct because it's hard to identify. So what do? We measure several variables, several things we can observe. We put them together into a scale and we say this is a scale for X construct. And another, in this line, factor analysis models, item response models come in very handy in assessing these scales. So some of the things we use them for are trying to identify the number of dimensions underlying the indicators. And when I say dimensions, I say hopefully constructs, because dimensions can underlie indicators and they're entirely meaningless substantively. So I say hopefully those dimensions relate to constructs. And we also try to study how well these indicators that we have observed reflect the construct, and the extent to which this item response data reflects certain measurement ideals. So I'll give an example of what that means. If I gave a test of 10 items, and these 10 items are meant to measure math ability, I would hope that someone would higher math ability. Let's say item 1. I would hope someone who knows math more, let's assume person A knows math more than person B. I would hope that person A does better on item 1 than person B. That's a reasonable assumption. So we use these models to assess the quality of the data and how well they match certain measurement expectations ideals. And as I said, I'll talk about this from a regression perspective. So let's go right to it. I think I'll use a number of practical examples. So here's a sample data set. And on the left-hand side, we have the data set as we usually see it, right? Each row is a person. Row 1 is person 1, row 2 is person 2. And each person has answered 4 items. They have responded to 4 items. So we have 4 scores per person. If you're familiar with multi-level models, this is what some people call wide data formats. And the first step in thinking about this as a regression is to transform the data into the long data formats, such that each row is a person item. So if there are 4 items, then there'll be 4 rows per person in the data. So we have a long form data, yeah? Now, let's give some letters to this data. So we'll assume for now that the items are normally distributed. I mean, look at this, 2, 3, 4, 2, 3. It's unlikely discrete values are normally distributed, but let's just go with that. We'll assume they're normally distributed and we'll call them Y. And from person P, so some random person P in 1 to P, capital letter P persons, responding to item I. So there are several items, 1 to capital I. So these are the data we have, YIP. And this is a very basic model for this data. So if someone gave me this data and said, James, start describing this data, chances are this would be one of the very first few models I would run. And in this situation, I assume that the item responses, YIP, are a function of M subscript I. So MI is the mean of each item. So each item has some average. Some items people score highly on them. Some items people score lowly on them, yeah? Then followed by FP, and FP I call a person mean. So these are the scores of different peoples, the averages for different peoples. Some people score high, some people score low. And we have error. So this is what we don't understand or we can't explain at this moment. And generally in this model, the way we estimate it is we assume that the FP, which are the person means, are normally distributed with a mean of 0 and some standard deviation. This is what I think people call a random intercept multi-level model, fairly generic multi-level model. And the error are normally distributed also with a 0 mean and some standard residual standard deviation. Here, fairly standard multi-level model, FP is a random intercept. That's what we call it. You might ask, why do we assume that the means are normally distributed? There are so many rationales people give. Some stem from central limit theorem. Some stem from the idea that a normal distribution is a least surprising distribution if you make certain limited assumptions about the data. For some people, it's just a device. It's like a model-based device that I'm going to use because it has some nice properties. Now, this fairly general multi-level model, actually, in this model, the FP, the person mean, if you think of this as a measurement model, the FP are actually factor scores. You can think of them as factor scores. They are the scores of each person on the construct. Does that make sense? And if you're familiar with EFA, these scores actually have a name. They tend to be called regression scores, if you're familiar with EFA. So this is a fairly basic multi-level model that actually corresponds to a particular kind of measurement model. Now, we write this model and just change a very simple thing. I say F, I assume it's normally distributed with 0 and L as its standard deviation. Instead, I say it's normally distributed with a mean of 0 and 1 as a standard deviation. And I move the standard deviation to the front of the factor. Yeah. So just a simple transformation, very simple basic algebra. Now, when you do this, this structure is fairly strange in regression. I never see people write this out in regression. But this structure is actually quite standard in measurement. In this situation, the standard deviation of the factor is actually what we call the factor loading. So in this, if you look at this model, L is the coefficient for the factor score, right? So larger values of L mean a stronger relation, an average between the responses and the factor. Smaller values of L mean a weaker relation. In factor analysis, we would call L a loading. That's what we would call it. So this is still the same original multi-level model, but we have taken one of the parameters, the random intercept standard deviation, and we can interpret it as a factor analysis loading. Now, in this model, it's fairly different from the factor analysis models we run, because in this model, all items have the same value of L. There's no, if you look at L, there's no distinction by item. It's L, one L that we have, a single L value. Now, to make this a bit more typical, we will modify the model a bit. So here, what we're doing is L now has subscript I. So the coefficients of the factor coefficient actually changes by the item. And the error, another change is that the errors have, the standard deviation now has subscript I also. So the error standard deviation changes by the item. This is what you might call a non-linear multi-level model with heteroscedastic error terms. This is fairly involved language, but this is what you might call it. It's non-linear because you have a product of two parameters here, Li and Fp. So usually we think of that as non-linear models. And in this model, if you look at it, the idea here is that items that have stronger values of L will be more strongly related to the factor, because that's the coefficient. So larger L, stronger relation, lower L, weaker relation. This is the general idea. So this model here actually is a very standard unidimensional factor analysis model. If you run a factor analysis in your typical software for a unidimensional factor, so a single factor model, this is the model you're running. And it's a multi-level model, not too standard because of this multiplication of parameters. The idea here is if you're familiar with regression models and you're quite proficient at that, then it's a very simple step to move towards measurement modeling, because we are relying on the same basic techniques, the same basic models. A multi-level model here is also a standard CFA, where you have, this is a diagram of it. So this model here corresponds to this diagram. The oval is the latent variable or factor, and it has an influence. We assume that the I factor influences each indicator. The value we put on this influence is what we call the loading, and that's the value here, Li. And then so the items also have some unexplained portion, which I call the error variance or SI squared. So these two models correspond. It's the same model. Now, why would we do this? Why would we think of these factor analysis models as regression models? Well, one of the reasons that convinces me the most is we can fit these measurement models into a generalized nonlinear mixed model framework, where you can basically think of them as regression models. And the practices that you know to do with regression, the different techniques of thinking about covariates and how we can think of them in interesting ways, how we can think of predictors and their influences in interesting ways, we can start to bring them into measurement modeling. So there's a text by DeBoek and Wilson, and in this text, the form of measurement model is a very descriptive kind of measurement modeling, very flexible, very relaxed. You can start from this very standard measurement model and innovate in very interesting ways, if you think of it as a regression. You are not constrained to the models that are pre-programmed into your measurement model software like M+ or Lavan. You can think very broadly about them. Well, another reason that is quite potentially relevant for this audience is you can start to incorporate different distributions for your indicators. You can very easily model mixed item formats, if you think of it this way. For example, normal distributions for normally distributed data, student T distributions, if you think you have outliers, Poisson for counts. And all of this is computationally easy in a Bayesian framework. If you're using modern Bayesian computation, this stuff is relatively easy, I would say. Now we start with this basic model, but we run into a problem, local independence. That's the very first problem we hit. So in this model here, there's an assumption built into the model. The assumption is that the relation between all your indicators depend on the latent construct. The reason the indicators that you observe are related is because there's a construct that influences them. There's no other reason for them to be related. Now, in truth, if you ever analyze data like this, you'll find that that assumption is almost never met. Indicators are almost always extra related beyond the implied relation via the constructs. If this is violated, well, the effect of violating this depends. You can have gross violations, like you don't even have a unidimensional model, you don't have a factor model, and you can have weaker violations where things may not be too impacted. But what are some of the sources of these kinds of violation? Now, I will assume in this discussion that you at least reasonably have indicators that measure a construct. So unidimensionality is a believable assumption. That's an assumption I'm making in the discussion that follows. Well, one of the most common things I see in psychological skills is item pairs that are very related. So question 1, do you feel sad today? Question 2, do you feel depressed today? And for most normal human beings, they see those questions and they think these are the same thing. They struggle to differentiate them. There's someone out there who can, because those items don't always have, like someone might respond 4 to 1 and 5 to the other. But for most people, it's like, how do I differentiate these two? Well, in that situation, you're creating a relation between items that goes beyond the concept of depression in this example. A simple solution in that context might be to just dump one, or find a reason to justify the presence of these two very closely linked items. Now, another reason that is fairly common is when you create a unidimensional scale, usually any construct can be broken down into subconstructs, usually. And even though we create a unidimensional scale, usually when you're selecting your items, you're tapping into the various aspects of the construct. When you run a unidimensional model, the constructs tend to cluster by those sub-aspects of the constructs. And that leads to a violation of the local independence assumption. Because now those items are not just related through your overall constructs, they are related through the sub-constructs. So that's a violation. Another source of violation is non-substantive factors like method effects. So let's assume we have a test of 20 items and 5 of those items stem from the same passage. So it's a reading test. Question 1, answer. Question 2, answer. The last 5 questions on the test, you have to read a passage, and then from that passage, answer 5 questions. Those questions, the responses will be they are related in ways beyond the general concept of reading. They are related because they stem from the same passage. That passage is likely not substantively useful or interesting in any way, but it creates an excess interrelation between those items. And so this can also lead to this violation of local independence. Now, the last reason I'll discuss is, I think this, here I mentioned 2 concepts, adventitious error and unidentifiable minor factors. These are very broad concepts, but the idea is, this is quite interesting. When we develop instruments to measure constructs, we're usually thinking of some ideal population in which this instrument is unidimensional and measures the construct. Now, when you go to deliver this construct, it's possible the day is hot. You give it sun and it's a hot day, or it's a chilly day, or you're working with a sample of just students. In my field, a lot of psychology work, people work with just students, or you're working with a clinical population. What happens is the ideal population you have when you develop the construct is different from the specific population that you collect data from. That specific population, the relations and the variables for them are not going to match the ideal population because they're unique in some way. Some of you have talked about working across different cultures. You tend to see this. So this gives rise to the concept of adventitious error. And from this perspective, you should almost never expect measurement models to fit perfectly, because every population, whenever you administer, you're administering to a specific population that is unique in its own way. Even if it's a random sample, there's still something special about the random sample, whether it's the measurement conditions under which you deliver it. We cannot fully have random sampling of every single factor that creates item responses. So we should always expect some amount of error, deviation from the model when we actually fit data. That's the explanation of adventitious error. Unidentifiable minor factors is similar. The idea here is that if people are answering questions on a scale, well, if it's a depression scale, it might influence their responses. If it's a cognitive scale, it might influence their responses. But there are other little factors here and there, so many of them that we can't account for, we can't possibly theorize, that are also influencing their responses. This is reasonable. I mean, if you think about it, it's very reasonable. It might be a hot day, it might be a cold day. Some might have shouted at them that morning. These are little minor factors adding up here and there that influence the responses people give. This will also lead to violations of local independence. When you test the model will not have acceptable fits. So these are some common sources of violations. For this last two, there are ways of handling them with Bayesian inference, but I won't talk about that today. I'll talk about some common solutions that try to maintain unidimensionality even when we have violations of local independence. So two common solutions we see in the literature that try to maintain, I say maintain in quotes because these are not unidimensional models, strictly speaking, but they still maintain unidimensionality theoretically or conceptually. One is second order factor models, the other is bifactor models. And I'll focus on bifactor models, but first talk about both of them briefly. Now on the left, we have a sample second order factor model. In this model, we have a general factor, an overall factor. This is the construct of interest. We assume that this construct influences some lower order factors. The construct causes the lower order factors, and then those lower order factors cause the observed responses, the item responses that we record. So this is a higher order or second order factor model. On the right, we have a different structure, which is a bifactor structure. In this structure, we call it bifactor 2. Every item, or the items here are influenced by two factors, a general factor and a specific factor. So these two models, they're conceptually different, and you can see the conceptual difference in the applications. So second order factor models are quite common when people assume, well, I have a single construct here, but it has substantively interesting sub-factors. And so the construct influences those factors influence my items. Now, the bifactor is more common when the interest and the focus is almost squarely on the higher order factor, on the general factor. That's your substantive interest. You really are aiming for unidimensionality here. Sometimes those specific factors, the F1, F2, F3, they might be substantively important, but you want to focus on the general factor. This is when people will often deploy the bifactor model. Another thing about the bifactor model is you can use it to account for non-substantive effects like method effects. So certain items stemming from the same passage. That makes sense in this context. I'll elaborate more on the bifactor structure yes.
Why are there stars with your map?
I'll elaborate that very soon. Yes, it's on purpose. There's a reason why they are not stars, asterisks on F1 to F3 on the left. They are asterisks on F1 to F3 on the right. Now, we usually present these models as different, but they're actually quite related to each other. If you make certain adjustments to the second order factor model, it is mathematically equivalent to the bifactor model. And you can reduce this special second order factor model in such a way that it becomes the simple one. This is what allows you to make model comparisons between both models, nested model comparison methods between both models. So basically, parameter estimates from the two models can be simple transformations of each other. Can be, not always. Now, in the bifactor model, we see this F1, F2, F3, they have asterisks on them. That's because they are not actually the real, especially if you're dealing with substantive factors, they are not the real factors we're thinking about. For example, in the bifactor model, we assume that all these factors here are uncorrelated. Now, if you're thinking of a higher order construct and say, okay, so intelligence, and you have visual intelligence, verbal intelligence, speeded intelligence, we would assume that those are correlated. Speeded has some correlation with verbal, has some correlation with visual. In the bifactor model, by default, the assumption is all your factors are uncorrelated. And there's a reason why. Now, in the bifactor model, looking at this example here on the right, we have the general factor and we have 9 tests of the general factor. Visual, cubes, lozenges, and the tests cluster by substantive factors. So the first 3 belong to visual, specific intelligence. The second 3 belong to verbal. Now, this visual factor here is not truly visual intelligence as we think about it. It is more visual intelligence that is residual, that is separate from general intelligence. It is the aspect of visual intelligence that is unique to visual intelligence, but not general intelligence. And that is not the visual intelligence we regularly conceptualize. When you're thinking of visual intelligence, you're thinking of visual intelligence that has some correlation to general intelligence and other forms of intelligence. But here in the bifactor model, the visual intelligence here is the visual intelligence it's unique, separate from the general factor. So people sometimes think of it as a residual factor. It is not the original factor. On the left-hand side, it's much simpler. You have a single, this is an example from an ADME paper I picked up. I don't know what's going on here, but I have some idea. You have several tests that are meant to be reflections of executive functioning. Now, the last 5 indicators have this clock thing in them. So I imagine that the items have to do with a clock of some kind. And so a clock as a concept shouldn't be related to executive functioning, I imagine, but it creates a special relation between these items that has nothing to do with executive functioning. So in this situation, we use this clock method factor to capture the relations between these items, the extra relation between these items separate from executive functioning. Make sense? Now, the interesting thing here, which I'll get to very soon, is if you look at this, we said that the loadings represents the relation from factor to item. In this model, you have 0.41, 0.67, 0.6. Are we suggesting that some of these items are more clocked? They represent a clockedness trait than others because the loadings are different. So that suggests that they differentially relate to this clockedness trait. And does that make sense? So it's an interesting thing with bifactor models. And I'll talk about this very soon. There are lots of controversies about these models. First thing to mention is that it's a very old model. So I think there's work from Spearman in 1904 trying to establish general intelligence and bifactor. If you give several tests to people, the performance on those tests stem from 2 factors, the general factor of intelligence and specific factors, so bifactor. And one of the very classic data sets on bifactor analysis is from 1936, Holzinger and Swinford, and I'll demonstrate it here. So it's a very old model. but for a while, people didn't talk about it much. In the late part of the 20th century, there was some work on testlets in education. But recently, it's got very popular. You see a lot of papers using bifactor models. And the old model, I talk about G, general factor of intelligence. Recently, you see a lot of work on P factor, psychopathology. I think psychologists do this a lot with bifactor models. Now, these models have a lot of controversy. And so what are some of the issues? The first thing is bifactor models are very flexible, very, very flexible. Like when we fit models, we're trying to make claims about the relations in data. And the models are not necessarily true. They don't stem from some super truth out there. They are impositions we make. Now, bifactor models are quite greedy. They will twist themselves to match the patterns in your data. So they end up looking quite good on the basis of model fit indices. If we assess them using conventional model fit indices, bifactor models end up looking quite good relative to other options. And one of the senses I have is that a lot of measurement modeling, as I see it applied, is basically a model fit index game where people are trying to find models with the best fit, and bifactor models will win that battle often. And I think it is reasonable to say that model fit indices are not, it is unfair to place that responsibility on them to decide which models are valid or best to explain reality on the basis of model fit indices. I don't want to go into that much, but model fit indices are not best for that, is what I would say very briefly. Some other issues with the bifactor model is, what does the general factor actually mean? So if you look at this structure here, we claim that it's in this example, this is meant to be intelligence on the right. And we claim that the general factor is general intelligence. Well, that is just a claim. It's an imposition on data. Is that really the case? There's some work that actually shows that sometimes the general factor just basically, if you have, let's go back to this example. Let's say there were 5 factors, 5 items for visual and 3 for the other 2. There's some work that shows that the general factor tends to latch onto the visual factor, latch onto the specific factor that has the most items. And really your general factor is just measuring that specific factor. So it's not always clear that the general factor is really the general factor you claim it to be. Another question is, what should we expect the loadings of the general factor in bifactor models to be? So the relations between the general factor and the items. Well, ideally, we would expect them to be non-negligible. So we would expect some substantial relation between the general factor and the items. But if we don't find that, if we find them to be negligible, what does that imply? Does that mean this indicator doesn't reflect the general factor? And the second thing now, the second point there is about predicting the relative magnitudes of loadings a priori. I actually think that if you're doing good measurement, you should be able to, ahead of fitting your model, rank the loadings, rank the items in how well they should reflect the factor. So if you have 9 items and they are meant to reflect intelligence in this example, visual, cubes, lozenges, you should have some theory of which ones should have better loadings than the factor. If you can't, why do you let them be different? This is a question I have. If you cannot explain why they should be different, and if you cannot rank them, why let them be different? Because if you fit a model to data, it will give you results. Whether those results are believable, to me, it's a question. And I think if you understand your construct really well, you should be able to say this indicator is a very salient indicator of this construct relative to this and that indicator. Predict it ahead of time and test it when you run the model. It's I don't know if other people say this, but this is a belief I have. So the loadings on the general factor, should we be able to predict their relative magnitudes ahead of time? Because if you get a result and, okay, item 1 has the strongest, item 2 has the weakest, these values are just based on correlations in data. How do you know that they have meaning? If you can predict them ahead of time and they match, to me, it gives you a good sense that, well, maybe this factor is actually the real thing. Additionally, what do the specific factors mean? If you're using specific factors to capture method effects, then it's easy. But if you're using them to capture substantive effects, it's hard. You're getting at this residual substantive factors. And what does that really mean? It's not so easy to tell what that means. And when we fit bifactor models, by default, I said earlier, the specific factors are uncorrelated. But you sometimes see bifactor applications where people allow the specific factors to be correlated. And for me, conceptually, that's challenging, because if you say this is a specific residual factor that is separate from the general factor, why should it share correlation with other specific residual factors? What is in that correlation? So that's a question I have when I see certain bifactor models where the residual factors are correlated. Also, should we have expectations for the residual factor loadings? So should they be small but non-trivial? Should they be large? If you're looking at method effects, should all the loadings be constrained to be equal? For example, the clock example, can you claim that item X reflects clock more than item Y? And should we constrain those loadings to be equal? That's the question I would ask when you fit in these models. Another thing you find with bifactor models is strange parameter estimates. You see negative variances, non-convergent models, strange things, because they're relatively complex. So sometimes they're a big ask of the data you have. And the last one, quite important, is the general factors may actually not be reflective. This is a general issue with how we think of measurements. The general idea we have is there are factors, constructs, and they influence responses to observed items. But what if it's the other way around? What if a factor is a combination of the items? What if a general factor is a combination of the sub-factors? So the common example people give for this is socioeconomic status, and they would say socioeconomic status is a combination of different sub-factors. It is not the costs of those sub-factors, it is a combination. Well, that's a different measurement model from factor to indicators arrow. It's the reverse. And there's work that shows that if the reverse is true, if the items, the sub-factors are the ones that join together to form the general factor, or the items are combined to form the factor, using measurement models as we use them actually leads to very bad results. Okay. Using measurement models as we use them leads to very bad results. So the title of this paper is actually, I think it's called Worse Than Measurement Error. If you have sub-factors or items that form the general factor, so we think of those as formative indicators or composite indicators. If that's the case and use the measurements, these measurement models where we assume the factors cause the indicators, the results are actually pretty bad. So a bifactor model, what does it look like in a regression context? Because again, I'm trying to tie this all to regression. This is the data. Let's assume this data represents responses to 7 items. So each person appears 7 rows in the data, items 1 to 7. These items are all related to reading, but the last 3 items stem from the same passage. So in a sense, we expect them to be more interrelated beyond the concept of reading. In this data set, I would create a variable like this. So it's a dummy variable, right? Representing that passage for the last 3 items. This is the original model we started with. And this is how we would modify the model. We would introduce this set here. The G here is the dummy for the passage. Ki represents the loading of the item on this passage factor. And HP is the score on this, is the factor score for this passage. So it's an extended regression model here. And just as this specific factor for the passage is also normally distributed with a mean of 0, standard deviation of 1. It's similar to the original factor scores. So this is how we would form the regression for this bifactor model in this situation. Now, broadly, I would say, given the right machinery, I said that is Bayesian, but I don't want to be that strong. So e.g. Bayesian machinery, you can pretty much fit any of these latent variable models as regression. So this is an example here, fits in a bifactor model as a regression model. We can extend this in so many ways. You can fit any of these models as regression. And there's a text by Song and Lee that leans on this. It uses the idea of latent variable models as regression to do a lot of very interesting things. And I've seen work recently that places nonlinear relations between the factors and the items, the indicators, which can be used for diagnostics in interesting ways. However, the very standard approach of estimating measurement models is to usually rely on some kind of model implied covariance matrix where possible. Now, in the Bayesian context, this matters because it gives you two options. You can either fit the model using a regression structure where you're estimating factor scores, or you can work with this model implied covariance matrix approach. The model implied covariance matrix approach is actually, it gives more efficient estimates. Results are better in a sense. However, this approach is not extendable to all regression models. So the efficient approach works for only a subset of models, but very common models, while the regression approach could work for virtually any kind of model. One thing to note about the regression approach, some of us may be using BRMS in the next few days. When you treat these models as regression, the likelihood, which is eventually often used for model comparisons, is calculated in a different way than typical. So this is something you may have to watch out for. The two ways of calculating the likelihood, which is then used to calculate the information criteria, lead to substantively different types of model comparisons. And finally, when you're using measurement modeling and thinking about them as regressions, the bifactor structure also provides a very convenient approach for correlating variables. So if we go back to this model here, we have a correlation between categories animal and categories vegetable. Another way to do that is just apply a bifactor structure, a special factor for those two items. It's a very convenient approach to correlate those variables. And now I think I'll conclude with some applications, two example applications to demonstrate some of this Bayesian inference with factor measurement modeling and regression. So the first one is a very, very classic bifactor example, Huizinga-Swineford. I'm using a reduced version of the data set that's fairly common. And these are the items. There are 9 items here, or they're not actually items, they're test scores. So there are 9 test scores, and they are believed to reflect general intelligence. Now, when I'm modeling data using Bayesian methods, I often start by visualizing my data. If I don't have any strong, which is often the case, I don't have any strong subject matter knowledge of the data, I start by visualizing the data. I want to have a sense of the kind of data I'm looking at. So here in this situation, I'm going to go with the normal distribution likelihood for this data. I'm going to assume that's reasonable here. Now we have I showed 3 candidate models. The first one we have seen already, it's a bifactor model. We have general factor of intelligence, and we have specific residual factors for the specific kinds of intelligence. The second one is simpler, more common correlated factors model. I simply assume I have 3 factors, 3 specific factors of intelligence, and they are correlated. Here, visual, verbal, and speed ideally should mean what we think they mean. Remember, in the bifactor model, visual, verbal, and speed don't mean the natural conceptions of those factors. And the last one is one where I'm trying to show what is possible in the Bayesian framework. In this model, you will see that, well, visual goes to its 3, verbal goes to its 3, speed goes to its 3. But then you have all these arrows flying all around. In this model, every indicator is related to every factor. So this is actually quite similar to an EFA, if you think about it, where all the items load on all the factors. So here, every indicator reflects every factor. Now, why would someone run a model like this? Well, with this, what we have here in the middle is a very common model, and it assumes what we call simple structure. It's very clean. Every item reflects its factor. Paragraph comprehension has nothing to do with visual, absolutely nothing. It's exactly zero. The relation from visual to paragraph comprehension is exactly zero. Now, in real life, nothing is exactly zero. There's always something. It might be trivial, but there's always something. And what we find in models like this is those trivial relations kind of expand and they get sucked into the correlations between your factors. So let's assume visual is actually related to addition, but in this model, we haven't done that. That relation will get sucked into the correlation between the visual factor and the speed factor. So it will inflate the interfactor correlations. So in a sense, doing something like this, which is more flexible, which allows everything to relate to everything, leads to a more realistic view of the data. However, traditionally, you cannot fit this model. It is unidentified. But if you're using Bayesian modeling, you can do interesting things like attempt to shrink all those cross-loadings to zero. So in this situation, I penalized the cross-loadings. I put a prior on them that heavily suggested that these loadings are actually zero, while giving some room for them to be greater than zero or different from zero, whether positive or negative. In this situation, the specific prior was a kind of global local prior, which is quite a flexible approach. And so these are the results. The correlated factors model on the left, the model with all the cross-loadings estimated in the middle. Now, if you look at the results, we see, okay, reasonable loadings for these items on this factor, reasonable loadings here, reasonable loadings here. We constrain the data to be this way, so we would hope that these loadings would be reasonable. Now, in the second model, I have allowed everything to relate to everything while shrinking these cross-loadings, trying to encourage them to be zero. And what you see is that a lot of them are pretty close to zero. A lot of them. However, there are some that are not. So I should explain what these numbers are. The very top number is the estimate of the loading, and the two bottom numbers are the 90% credible interval. So those are the 90% range where I think there's a good chance, the actual value of the loading lies in that range. I think there's a good chance the loading is in that range. This is the uncertainty about the loading. And so for some of these, you can see that they are very close to zero, but here we have something that's different. Item 9 actually has a loading of 0.32 on the first factor. So this is straight and curved capitals. That's the test. And if you don't know anything about the test, if you just look at the description, it might make sense that straight and curved capitals has something to do with a visual factor. Yes, so the results here suggest that. The other thing to note is the interfactor correlations. From model 1, all the interfactor correlations have reduced in their magnitude on average from model 1 to model 2. So this is that point I was making. When we estimate a more flexible model like this, we get lower interfactor correlations, which we hope are more correct in a sense. Now, the last model is the bifactor model in this example. The first column shows the general factor loadings, and the next 3 columns show the specific factor loadings. In this case, here, we have specific visual, and the loadings are kind of strange. Negative, negative, positive. What am I to make of that? I really don't know. Can I call this a residual visual factor that is negatively related to visual items? I'm not sure. I don't know what to make of that. Another thing you see though is once you move beyond the first 3 items, everything else loads more strongly on its specific factor. So are these items actually reflective of general intelligence or these specific factors? In this example, one can argue that the general factor is mostly capturing visual intelligence, and the other items from the other factors don't really show up on the general factor. In my opinion, this is an unacceptable bifactor structure. I wouldn't accept this as a good result. Now, let's look at what model fit has to say about this. I use something called a PPP. It's PPP In this sense, it's a specific posterior predictive p-value that is kind of similar to the one you find in standard frequencies testing. And in that sense, usually people like these numbers to be large, greater than 0.05, greater than 0.1. By liberal benchmark, both these models are acceptable by the PPP. But recall earlier I said, I think it is too large a responsibility to place on this model comparisons and fit or fit indices to decide which models to use. In this situation, even though these two are acceptable, these results don't conform to what I would call a reasonable model for data. I can't explain the structure I am seeing. While for the structure in the middle, makes more sense. If I had to choose between these three models, given that this is acceptable, it has acceptable fits to the data, and the parameter estimates make sense. Okay, the second model is a much more believable model. I don't have a simple structure here. All the items relate to the factors in some ways. And importantly, item 9 also relates to the first factor. That's the conclusion I would reach here. And in this situation, I would not accept this bifactor structure because there's just too many things that I cannot explain. In a second example, I jumped into the ADNI data. ADNI 2, this is a baseline. I don't really know what I was doing, but you can always model data. But one of the things that is interesting is the richest models come from substantive expertise and some statistical knowledge. So hopefully by talking with some people in this room, I can come up with a much more reasonable and better model for this data. Well, one thing we note is in this data here, we have 15 items or 15 indicators, broadly speaking. And these indicators kind of look different. So, and all of them are meant to reflect the language. I believe that's the language domain in this data. So here, again, we are striving for unidimensionality, but we can expect that there may be some violations of local independence. So potentially bifactor structure is useful. As I said, I start by visualizing my data. The first thing I notice is that the items have different distributions. So the first two kind of bell-shaped, the third one isn't. The third one, I believe, is the number of correct answers on a 30-item test. So for this data, you can't go above 30. And for the first three, I don't think you can go below 0. 0 is a lower bound. The first two, though, I think they're unbounded on the higher end. These are assumptions I made from looking at the data. Now, the last 12 seem ordinal, but something interesting about them is that for some of them, not all the levels are realized in the data. So if you look at this naming item, you only have, I think it's a sum of 5 different numbers, or how many you get out of 5. And if it's how many you get out of 5, you should have 0, 1, 2, 3, 4, 5, no. Yeah, 0, 1, 2, 3, 4, 5. You should have 6 response values, but in the data, we only have 4. 1, 3, 4, 5. That's all we observed in the data. So those are just some things to keep in mind from looking at the data initially. Now, when I'm modeling data thinking of them as regression, also using Bayesian inference, I like to assume realistic likelihoods for data, realistic distributions for the data I have. For example, something like this, there's no reason to think that is normally distributed. A normal data generating process could never give us something like that. That is unrealistic. So here I'm starting to consider what are the potential distributions for this data. First choice is, well, since the first 3 are seemingly continuous, though their counts, they're almost continuous, I can think of the first 3 as normal and the last 12 as ordinal. That's a simple starting point. What I think happens is the first 3 are actually categorized to create ordinal seeming data. But if you do that, then the question is, what are the cut points? Depending on your goal, practically, it may not really matter. But if you're trying to model data and use as much information in the data as possible, then maybe you don't do that. But if you're being pragmatic, there are a lot of things that may not really matter. if your goal is extreme pragmatism. Another option is to assume the first two items are normal, and that's reasonable, even though I know they can't be less than 0. They are count processes, and when count processes are high enough, you can approximate them with the normal distribution. So that's an option. But the last one, there's no way I can approximate that with a normal distribution. I will assume something like a beta binomial distribution or binomial distribution easily, which is the number of successes out of the number of trials. If you score 26 out of 30, then you succeeded 26 times out of 30. Here, a lot of people succeeded 30 times out of 30. And the last option is to assume all the items are ordinal from 1 to 15. Now, that's a bit interesting because if data are continuous, if we assume them to be continuous, then they are also by definition ordinal. If you say 1, 2, 3, 4, 5, 2.4, 2.6, 2.8, well, 2.6 we assume is greater than 2.4, is greater than 2.0, greater than 1.7. So if data are continuous, they are also ordinal. So we can also assume broadly that all of these, we just treat them as ordinal. And that's one option. So thinking about this is the model I didn't come up with this independently. I looked at some things and said, well, let's try this model for demonstration for this data. Again, with your inputs, I'm sure you might be able to come up with something richer. But here we assume the 15 items reflect this language domain. These 3 reflect a specific domain of, I don't know, naming animals. I am not sure. And the last 2 are also correlated with each other, extra correlated. So here, this is a bifactor structure with specific factors for the 11 to 13 and 14 and 15. This is the structure I'll work with. This is the regression model that accompanies the structure. I have a dummy variable for F1, that is G1I, and a dummy variable for F2. And so this is a regression model with 3 latent variables or 3 random intercepts that are uncorrelated. Now, this is the model for what we would call the linear predictor if you're thinking about this in a generalized linear model sense. Now, what do I do with this? It really depends on how I choose to model this data. This is the linear regression equation, but how do I use the result of the equation? It depends on how I model the data. In this case, I'm going to try an all ordinal approach. I'm going to assume everything is ordinal. Here, the base model I would use is what some people call graded response model, or if you're using the regression language, it's a nonlinear cumulative link logic mixed models with proportional odds assumption. That is, if you say that, that is actually very descriptive and precise enough that someone should be able to run what you have done. If you say graded response model, then you're in measurements world verbiage that only psychometricians might understand. Now, I earlier stated I would assume all the data are ordinal. And if we assume data are continuous, then they must be ordinal. Now, the problem is with ordinal data, we actually estimate the discrete observed data. We estimate parameters for each change in the variable. So if you think about a continuous variable can change an uncountable number of times. It could be literally any number, right? So if you're estimating parameters for each change, what we call threshold parameters, you can end up estimating an infinite number of parameters. That's not realistic. In M+, it actually limits you to 10, I think, or 9 thresholds. But now we can borrow something from the regression literature. There's a paper that suggests that if we have a whole large number of thresholds to estimate, we can actually approximate all those thresholds using splines, which allows us to model, which allows us to create non-linear functions. So if we have 1,000 thresholds to estimate, we can approximate them using splines. That's a potential option. And that's actually what I apply. Something like this can lead you to a kind of arbitrary distribution factor analysis model. Because if you can always assume the data are ordinal, regardless of the number of levels, and we can always estimate the thresholds using splines, then you can create a factor analysis model for any kind of data in a sense. And I call it semi-parametric. It's interesting because ordinal regression in the 2-sample case, ordinal regression is actually equivalent to the Mann-Whitney test. So it's kind of like a parametric model that is equivalent to a non-parametric model. So this kind of ordinal factor model that can take any kind of data in theory is kind of like a semi-parametric factor model in a sense. And briefly, I described the model. So here, instead of estimating any uncountable number of thresholds or large number of thresholds, I approximate them using 18-piece splines. Basically, instead of estimating for every change in the data, I approximate 18 parameters instead. And I apply shrinkage. Hopefully, over the next few days, we will learn what that is. But the sense here is if I'm going to estimate a large number of parameters, that can lead to overfitting, noisy estimates, shrinkage, or penalties, or reasonable priors. I can use them to regularize, to stabilize the estimates so that they're not so variable, so that they're not so noisy. And so I do that for my continuous variables, then I use regular thresholds for the others. I use Stan, a software to fit this model. And the first thing I show here are just this is a model diagnostic plot. When you run Bayesian models, we are relying on computational methods that are meant to approximate the posterior. And the degree to which they do that is always in question. Sometimes they are successful, sometimes they're not. So we have to do a lot of model assessments to see, well, are you doing a good job of approximating the posterior? And this is one of the checks we use. These are called trace plots. And here they look uninformative, I guess. There's no clear pattern. They just all oscillate about a steady point, which is good. When you see bad trace plots, you will know, I think. But this is just an example of a check we would do after running a model. And these are some of the parameter estimates. Here, I visualize some of the threshold parameters that I estimated for the ordinal variables. I noted originally that for the ordinal data, not all the levels were visible in the data, right? So going back to commands, only 5, 4, 3, 2, 0 were realized in the data. No one responded to level 1 in the data. Now, when I fit the model, I actually assume that a level 1 response is possible. And I estimate a threshold for the change from 0 to 1 and 1 to 2. There's no data, I have no data to estimate this threshold here. But in the Bayesian model, when you supply prior information, you can actually estimate parameters for which there's no data to estimate them. Again, the parameter results you get from a Bayesian model, like combination of two sources of information, data, prior. If there's nothing in the data, we can lean on the prior. And here, why that's important is because if I'm building a model for data, I want to be able to use that model to learn about the data. I want to draw inferences from the model. I want to use the model to describe the data. I want to use the model to describe the larger phenomenon I'm studying. And to me, when I'm doing that, it's important for the model to actually match true realistic processes. In truth, someone somewhere will respond to category level 1. In this data, we did not observe it, but someone somewhere is going to do that. So I want a model that has the capability to produce such theoretically possible data. And so these are several thresholds that we couldn't estimate in a traditional frequency system model that we can in the Bayesian model with the introduction of prior information. And for the continuous data, this is a kind of plot, a model diagnostic plot that allows us to see how well the predictions from our models, the posterior predictive distribution can generate data that is similar to the data we already have. And in this case, I think the points here is the point estimates from the model. The line range is the uncertainty about that estimate. And here we are seeing that the data the model generates is able to match the patterns in the original data. And so that builds my confidence in this model. This model is somewhat realistic. Here for the continuous data, it matches the pattern. This here is kind of bimodal, and you can see it does a bit of bimodality here, very slightly. And while this one is extremely skewed, and we're able to match it also using this ordinal approach. And finally, the loadings. I have grouped the loadings. On the left, you have the unstandardized loadings as I estimated them. On the right, I tried to standardize them, which I think people like standardized estimates for a variety of reasons. And at the bottom, we have the bifactor loadings. One thing I did, but did not note earlier, is I constrained the specific factor loadings to be equal. So camel, lion, and rhino, they are all equal. Those loadings are equal. Theoretically, there may be reasons not to. That's something that will be informed by like subject matter expertise. And in this situation, when I look at camel, lion, rhino, their loadings on the main factor are larger than their loadings on the specific factor. People will often interpret this to mean they are more reflective of language than they are of this specific factor that puts them together, which is good. However, certain items have quite unremarkable loadings. This one is quite noisy, read. So when I say that, I have a question. Is that what I expect? Should that read indicator be that weak an indicator of the language domain? I have to ask that question and come up with an answer. And so these are some of the parameters we get. I should have mentioned the ranges here are the 90% credible intervals. So they demonstrate the uncertainty around these parameters. So in doing this, I've hoped to capture some of the steps we would go through in the Bayesian process, try to model one. It's poor, I think, because the subject matter expertise is missing. And that's actually one thing that can make Bayesian modeling very rich. We can incorporate the knowledge experts have on these phenomena they're studying. Here I can't because I don't know anything really. And I will round up. So generally, the bifactor structure is useful for arguing for unidimensionality, but it warrants care. You cannot just fit a bifactor model, get the fit indices, and be done. No, you have to examine the estimates. They should make sense. If they don't make sense, always bear in mind that the bifactor model is kind of greedy. It will find a bifactor structure in the data of some type, and it will have good model fits. So it is up to you to question the parameter estimates you're getting from the model and be sure that they make sense, they are interpretable. Otherwise, you're just playing with correlations, I think. And thinking of measurement as regression allows for opportunities for thinking of measurement in very broad ways. We don't have to be limited to the very standard default models for which papers exist. When we have item response data, we can focus on the peculiar data we have and build a measurement model that is specific to that data and its generation process. We can incorporate the information we have as experts and use that to build rich models, rich measurement models. One of the important contributions of measurement theory, I would say, is that anyone with regression knowledge can model data in flexible ways. That's easy to do. But there are certain principles that we should assess in the data. So for example, the behavior of our loadings. Anyone can fit a model that has loadings, but what should we expect of those loadings? Another example is the relation between the factors and the items. What should we expect of those relations? This is where the measurement principles come in handy. But regression provides a very broad framework for thinking about measurements and modeling of forms of data to fit particular specific purposes. Thank you. I hope to learn a lot about your field over the next few days, and yeah, thank you. Oh, yeah. Not a programmatic one, but one like your visualization. Oh, I closed my.
So not a programmatic question, but the visualizations you gave are pretty awesome. So like the loading comparison and then looking at the threshold estimation. Were those all built ground up, or some of the packages that you used spit those out?
Ground up, mostly.
Okay.
Yeah, this is not ground up, but most of this is ground up. Yeah. Yeah, I think generally communicating statistical results, it's a thing that you just keep trying and keep learning to do better. Yeah, so a lot of ground up work. Yes. Okay.
Any other questions?
Thanks, James, for the great presentation. I have just a quick clarification question. So if you go to page 7, where you introduce the relationship between the latent variable model and regression, where you show the residual, yeah, the item error, this one is okay, the equation up there. So you have a sub I in S. So I was just trying to wrap my head around this notation here.
Oh, okay.
Because you have this item mean and item loading, so that means each item has 2 parameters already in this parameterization. But then in terms of residual, is that an item level parameter or is just a general parameter?
Can you repeat
okay.
some aspects of the question?
Yes. So the question is on the notation on the screen right now, the error is assumed to be normal, 0 with S sub I. And what is this? I believe the question is for me to elaborate a bit more on this notation. So for each item, in this model, we basically have 15 parameters in the conventional sense: item intercepts, item loadings, and item error standard deviations. So the S sub I is meant to be the standard deviation of error standard deviation of an item, and sub I is supposed to be that it varies for each item. That S value varies for each item. That's the notation. So SI is S1, S2, S3, and S4. Yeah.
So that means each item will have 3 parameters. So this model is not equivalent to a 2PL model.
Each item will have 3
Or
parameters.
Oh,
okay, good.
The standard deviation somehow related to the loading,
No.
like a transformation.
So in a 2PL model, you usually don't have the error standard deviations, right? But this is equivalent to a 1-factor continuous CFA. Confirmatory factor analysis. There we would have varying error standard deviations, varying loadings, and varying item means. So yes, it's not because in the 2PL model, in the IRT world where we focus on binary or ordinal data, we don't have error standard deviation parameters, or they are fixed in some way or constrained based on the model. Yeah. Yes.
So can I see if I got that?
Okay.
So if you're looking at an IRT world that builds on dichotomous items, where you either get it right or you get it wrong, we can have this model be what's called 2-parameter logistic model. And the reason for that is that we don't need to worry about your S's in that particular model because they're already accounted for because it's only dichotomous data. So this is more like if you had hypothetically a continuous indicator.
So it's an interesting when you get to binary, because you're using something like logistic, or to repeat the question, if you're in the binary world, the question is, do we need to worry about the error standard deviation? It's accounted for in some way. Is it already accounted for in some way in those binary item response models? And the answer is yes, in a sense, because when you get to logistic regression or probit regression, which underlie these models, we actually have fixed assumptions about the errors. So in a logistic model, well, let's go with the probit because it's easier. In a probit model, the assumption is that the error is normally distributed, means 0, standard deviation 1. Probit model is actually equivalent to assuming a continuous process with a normal distribution error, means 0, standard deviation 1, that has been dichotomized at some point. Now, because we don't have that underlying continuous process, we just make certain assumptions about the error. In this case, it would be N01. The interesting thing, though, is that because we don't have these error parameters, the loadings and the discriminations actually have an interesting relation to the error parameters. If the error parameter is, if you have an item with a lot of variance, then the loading will also be scaled up. And if you have an item with smaller variance, the loading will be scaled down. In a sense, in the item response theory models, these parameters like the loadings, discriminations, are scaled up or down depending on the latent error. We don't know the latent error, we don't estimate it, we just assume it's fixed. Whereas because we assume it's fixed, the parameters related to each item are scaled up or down depending on that latent error. So somewhat, I don't know if there's a simple way to explain it. If there is, I'm not able to do it because it's related to this issue of unobserved heterogeneity in binary models and ordinal models. Yes. It's taken care of by the loadings.
Yeah.
Yes.
Great. Well, little complicated. So thank you so much.
Yeah.